Okay, so let's look at some questions that go along with the first video for this week. So number 3 right here, which of the following best explains why the normal boiling point of CCl4 is 350 Kelvin, which is greater than that of CF4? So we see boiling point, we should automatically start thinking about intermolecular forces because they are what determine boiling point. You know, how hard it is to get molecules to leave their liquid phase for the vapor pressure to equal the atmospheric pressure. That's when we boil. So when we look at these right here, CCl4 and CF4, they're both tetrahedral, they're both non-polar. All they have are LDF. So the CCl bonds are less polar than the CF bonds. Well, that might be true, but that has nothing to do with boiling point. The mass of CF4 is greater than that of CCl4. Who cares? I don't care that the molar mass is greater. The bonds are covalent, whereas these are ionic. That's false. There are not ionic bonds here. The answer is C. The electron cloud in CCl4 is more polarizable than that of CF4. Electron cloud polarizability is the technical way of discussing LDF. Okay, so more polarizable means there are more electrons and the LDF is greater. The greater LDF is the reason why CCl4 has a higher boiling point. Number 4, which of the substances exhibits greater hydrogen bonding in the liquid state? So we would need to do some quick, little Lewis structures here, but we can mark out a couple. C2H4, hydrogen's not directly bonded to NO or F. Here, the oxygen is bonded to a carbon and a carbon. It's not bonded to NO or F. When we look at CH2F2, the hydrogens are not bonded to the fluorines. In N2H4, hydrogen is directly bonded to nitrogen. It's the only one of those that can hydrogen bond. The vapor pressure of a heavier substance will be lower than that of a lighter, all other things being equal. Now remember, the greater the intermolecular force, the lower the vapor pressure because it's harder for that molecule to leave its liquid state and escape as a gas. Okay? It's just a lot harder for that to happen. So the vapor pressure of a heavier substance will be lower than that because the molecules are more polarizable. The bigger you are, the more electrons, the greater the LDF, the more your electron cloud is polarizable, and that's going to lower the vapor pressure. So number 9, the liquefied hydrogen halides have their boiling points given. The high boiling point of HF. So all 4 of those are polar. They can all dipole-dipole. They all have LDF. But we notice HF is the greater boiling point by far. And the reason for that is HF can form hydrogen bonds and the others cannot. So this has 3 intermolecular forces. Those only have 2 intermolecular forces. Notice HI has the higher boiling point because it would have the greater LDF of those 3, and they all 3 can dipole-dipole. The melting point of MgO is higher than that of NaF. Explain this. Now, this goes back to ionic, which I did not talk about in the previous video, but I did show the equation. So remember, it's charges on top, and it is the distance between them squared on the bottom. And the first thing we look at are charges. 2 plus, 2 minus, 1 plus, 1 minus. So the answer to number 14 is C. Mg2 plus is more positively charged than Na. O2 minus is more negatively charged than F minus. Both of those reasons cause the ionic force of attraction in MgO to be greater than that of NaF. Because it's a greater force of attraction, it's harder to separate them. It's harder to melt them. So there's only one problem on this page. We're given 3 Lewis structures and their densities. So this has the lowest density, water in the middle, and CS2 has the greatest density. And then we're given these pictures, and we're told we mix all this up, and we want to pick which of these would be how the liquids would settle and mix together. So when we look back up here, water is polar. This right here, which is methanol, is polar. CS2 is nonpolar. Well, light dissolves light. The two polar would mix together. The nonpolar would not. And the nonpolar is most dense out of the two of them, which is why when we look at these answer choices right here, we need water and methanol to mix together. They are soluble together. CS2 is not, so there would be a separation, and CS2 is more dense, which is why C is the answer. One problem on this sheet, we're given methanol and this long hydrocarbon. And which of the following statements explains the difference between the substances' boiling point? Now, this is a discrepant event. This can dipole-dipole, it can LDF, and it can hydrogen bond. Over here, this cannot dipole-dipole. Hydrocarbons are nonpolar. It does have LDF, and it cannot hydrogen bond. But notice, the boiling point is greater than the boiling point here. So apparently, this LDF is so great, it's greater than the combination of those three. So when we look at our answer choices, hexane has the higher boiling point because of the polarizability of its electron cloud. It's talking about its LDF being way, apparently big enough to have a greater cumulative effect than those three. So B is our answer. So, which of the following statements accounts for the increase in boiling points amongst the noble gases? It's the London dispersion forces. Number 17, which of the following statements best accounts for the difference in solubility among the noble gases? So, the gases become more soluble as the molar mass increases because they become more polarizable. Thus, the amount of dipole-induced dipole forces increases. That's our answer. Number 14 down here is a solubility question. Based on the concepts of polarity and hydrogen bonding, which of the following sequences correctly list the compounds above in the order of their increasing solubility in water? So remember, water is polar, and water can hydrogen bond. Okay. When we look at X, it's just a hydrocarbon. That's nonpolar. It is not going to have a high solubility with water. This is a hydrocarbon with OH, so that makes it polar and it makes it able to hydrogen bond. Here's a hydrocarbon with two OHs, so it's even more polar and it can hydrogen bond more. So the answer to 14 is D. X has the lowest solubility because it's nonpolar. Y and Z have higher because they're polar. Z has the most because it can hydrogen bond more with the water. And to finish, okay, we're given these compounds and molecules and asked to label them based on their boiling points and then fill out this table. So the boiling points go from the lowest boiling point all the way through to the greatest boiling point. So let's check these out. ICl is covalent, nonmetals. NaI is ionic. Br2 is covalent. Cl2 is covalent. H2O2 is covalent. LiCl is ionic. Carbon is special. I'll talk about that on a video in an upcoming week. I'll just briefly talk about it here in relation to this answer. So remember, in order of magnitude, ionic is considered greater than covalent. So we're going to start with the covalent first. So Cl2 and Br2, they are the smallest. They also are nonpolar. They cannot dipole-dipole. So both of these only have LDF. Cl2 has the fewest electrons. It has the lowest boiling point. It's the easiest to separate. Then Br2. Now our next two are going to be our ICl and our H2O2. Both have LDF. Both can dipole-dipole, but H2O2 can hydrogen bond. So it would have the boiling point greater than ICl. So now our ionic, so LiCl and NaI have the same charges. So when we look at the charges in the numerator, that's not going to help. So we got to look at the distance separating them in the denominator. So the smaller they are, the closer they can get, and the greater the boiling point, the greater the ionic force of attraction. Li is smaller than Na, so Cl is smaller than I. So LiCl has the greater boiling point compared to NaI. The greatest one here is actually carbon. We'll discuss it in another video. Carbon can do something called network covalent bonding. And so it can be in graphite, or usually we think of it as in diamond. As far as conductivity goes, none of the covalent can conduct electricity. There are no ions. The ionic can conduct electricity if they're melted or if they're dissolved. And then diamond cannot at all. And solubility in water, because these only have, these are nonpolar. They are not soluble in water. These are polar, so they can. Ionic usually are, unless you're told otherwise, and diamond is not. And these two quick little questions at the bottom. It wants to explain why solid silver and liquid silver are good conductors of electricity, whereas solid silver nitrate is not a good conductor, but when it's melted or dissolved, it is. Well, silver is metallic bonding. We'll discuss that in another video. Mobile electrons. So because the electrons are free to move around in its solid form, it can conduct electricity. We melt it, same thing. Silver nitrate, though, ions cannot move freely in the solid, but if we melt it or dissolve it, the positive and negative ions can float around, so this can conduct electricity. And to finish, why is water's boiling point higher than H2S? Here are all of water's. Here are H2S's intermolecular forces. Water can hydrogen bond and H2S cannot. Therefore, water will have a higher boiling point due to greater intermolecular forces.